Hello viewers, welcome to this next lecture on the NPTEL MOOC course on mathematical portfolio theory. You would recall that in the previous week we talked mostly about utility theory and we talked about what are the characteristics of utility functions, particularly in the context of the risk attitude of investors. And then we talked about maximization of expected utility in terms of its definition, and we talked about the two important concepts extending the basic definition of utility, namely absolute risk aversion and the relative risk aversion, and we looked at some common examples of utility functions in the context of the preceding discussion on the properties that risk neutral or risk averse investor who is also a rational investor, and we tabulated those properties. And then we were planning on moving on to the next discussion on using utility theory in the context of portfolio optimization. So, that is the topic that we are going to start off in today's lecture. So, as I said, we will talk about portfolio analysis using utility functions. So, when we talk about utility functions, this is something investor specific, and so we say that we let the investors utility function be denoted by some u which is f of w. Now, it can be shown that the expected utility of a portfolio. So, this is the utility function. So, consequently, you can calculate the expected utility of a portfolio, and it can be shown that it is a function of the portfolio's mean and variance of returns. Of course, in addition to possibly other parameters. So, in other words, the expected utility becomes a function of the mean and the variance of the wealth W. So, let me be more specific with this result, which gives a quantitative formulation of this. So, the expected utility of the wealth, this can be shown that as the function of the expected wealth plus f double prime of expected wealth divided by 2 factorial into sigma w square. So, the expected utility, which is E of E w, is a function of the mean, which is this, and variance, which is this term of the wealth W. All right. So, now by looking at the form of the result, one can immediately guess that this has been derived making use of the Taylor series. So, accordingly, we take the Taylor series expansion of the function u. So, that means we take the Taylor series expansion of this u of w about, now since I have the term E of w, so this indicates to me that I will take the Taylor series expansion about the expected value E of W. So, therefore, U of W, I can rewrite this as U of E of W plus W minus E of W, and this is F of E of W plus W minus E of W. And now we do the Taylor series expansion. So, this is going to be F of E of W plus F prime of E of W into W minus E of W, plus the third term will be F double prime of E of W over 2 factorial into W minus E of W whole square, and then I have the remaining term of nth derivative of E of W over n factorial into W minus E of W raised to n is equal to 3 to infinity. So, here I specify where f n is the nth derivative function. So, next we take the expectation of this relation. So, then the expected utility is E of U of W is equal to F of E of W. So, here W is basically the deterministic wealth level. So, its expectation is going to be F of E of W plus F prime of E of W, which again is a deterministic quantity. So, and within bracket I have expected value of W minus E of W plus F double prime of E of W over 2 factorial into expected value of this term here W minus E of W square plus summation n is equal to 3 to infinity. This term remains as it is. So, the nth derivative evaluated at E of W over n factorial, and then we have expectation of W minus E of W raised to n. So, now we approximate, that means we ignore the higher order terms, that means we ignore these terms here. We obtain that E of U of W is approximately F of E of W, and now remember that this term is something that is going to be 0, because E of W minus E of W is 0, and then we have F double prime of E of W over 2 factorial, and this term by definition this is sigma W square. So, this is sigma W square, and this term here this is ignored. So, that means that we have obtained our result that we had stated here. Now, we recall that the one period return on an investment of W naught. So, W naught which gives terminal wealth W t. So, that means you have a time window 0 to t. You start off with a wealth W naught and your terminal wealth is W t. So, W naught is deterministic and W t is random. This is given by the following relation. So, this will be W t minus W naught over W naught, and I will denote this by R p. So, therefore, E of W t from this relation is W naught into 1 plus E of R p, and we get sigma W t square is going to be W naught square into sigma p square, where E of R p introduced here and sigma p square introduced here denote the portfolios. So, the investment was on a portfolio. So, the portfolio's P's mean, return and variance of returns over the period respectively. So, thus we get, so what we had? We had earlier we had the relation E of U of W is approximately f of E of W plus f double prime E of W over 2 factorial into sigma W square. This implies that now instead of W we will have W t. So, expected utility of W t is approximately f of expected value of W t, which is W naught into 1 plus E R p plus f double prime of expected value. So, this is going to be again expected value of W t. So, this is again going to be W naught into 1 plus E R p over 2 factorial multiplied by sigma t W t square, which is W naught square into sigma p square. So, now we can say that since W naught is a given constant, the expected utility of the terminal wealth. So, this is the utility of the terminal wealth W t, and this entire term is then going to be the expected utility of the terminal wealth. This is a function of the mean, that is E of R p, and variance sigma p square, and there is a E of R p here. So, mean and variance of the returns, namely E of R p and sigma p square respectively. So, that is E of U of W t is going to be some function f of E of R p and sigma p square. So, let us now look at an example to elucidate it in a better manner. So, for this we will look at a quadratic utility function. So, let U of W be given by some beta of W minus gamma W square, where as indicated in the previous class, these coefficients, that is the parameters beta and gamma, these are positive constants. So, therefore, U of W t is going to be beta of W t minus gamma of W t square. Now, this can be written, remember W t is nothing but W naught into 1 plus R p. So, I am replacing W t with the beta term minus gamma into W naught into 1 plus R p square, and this can be written as A plus B R p minus C R p square. where A is equal to beta W naught minus gamma W naught square, B is equal to beta W naught minus twice gamma W naught square, and C is equal to gamma W naught square. So, from this context we can conclude the following. So, I will make 2 points here. So, thus the utility function that are quadratic in W t. So, that means if I consider the quadratic utility function, then they are also quadratic in R p. So, this term here. And secondly, also expected utility of the terminal wealth. What is this going to be? This is going to be, for the quadratic utility function, this is going to be beta W t minus gamma W t square, and by the linearity property this is going to be beta into E of W t minus gamma into E of W t square, and this can be written as beta of E of W t minus gamma into E of W t square plus sigma W square. So, what I have done here is I have made use of the fact that sigma W square is going to be E of W t square minus E of W t whole square. So, I have just made use of the fact that sigma W square is E of W t square minus E of W t whole square. So, therefore, the portfolio analysis based on the quadratic utility function is identical to the standard mean variance analysis. So, this means basically, for example, if I am trying to maximize the expected utility, then this would be the same as minimizing the sigma W square, for example. So, this is one place you can reconcile this with the mean variance framework. So, next we come to our normally distributed returns. So, the usage of the expected utility approach results in the investors maximizing their expected utility even in presence of uncertainty. So, suppose that for a portfolio P, the number of outcomes is discrete, then its expected utility is which will denote by expected utility of W p. This is going to be summation of the utility of the terminal wealth in the ith scenario into the corresponding probability of the terminal wealth in that scenario, where I have considered that there are k scenarios or k possible outcomes. So, where k is the number of possible outcomes and W t superscript I is the terminal wealth in case of the ith outcome, and P I W t of I is the probability of the ith outcome. So, this means that I have a k number of outcomes which I will designate it as I equal to 1 to k. Then the terminal wealth level for each of those ith outcomes will be given by W t superscript I, and U of W t superscript I will be the utility, and the corresponding probability of the ith outcome is denoted by P I of W t of I. So, then I basically this wealth W p of the portfolio, the utility of that is going to be given, rather the expected utility of this is going to be given by the definition of the expectation, where the random I have k number of random variables. So, U of W p takes k possible different values as a random variable, which will denote as U W subscript t superscript I with the corresponding probability being given by P I. So, this is something like summation random variable into the corresponding probability to get the expectation, and remember that this is for the discrete case. Now, alternatively, so we will take a q from here, the way the expected utility is defined here, and alternatively, when the outcomes are continuously distributed, the expected utility is given by expected U of W p. This will be given by U of W subscript t into probability W subscript t with respect to the random variable W t and going from minus infinity to infinity, where I have introduced this new notation P of W t is the probability density function for the terminal wealth associated with the portfolio P. So, this is nothing but just the continuous time definition of the expectation of a random variable. So, I can say that therefore, for any utility function U of W E of U W p, this depends obviously on P of W t, the probability density function. So, now let us look at a particular case. So, in case the probability density function is normally distributed, then it will be of the form P of W t. Remember that W t here is a random variable, is equal to 1 over square root of twice pi sigma of w subscript t into exponential of minus of w t minus e of w t square over twice sigma square w t. Okay, now let us move on to non-normal distribution. Of returns. So, let me first begin with a motivation for this. So, I state that there is empirical evidence, that means data based evidence, that asset returns are not normally distributed. It has been observed that the unconditional distribution of asset returns have non-symmetric, highly peaked and longer tail characteristics. There is a basic assumption that the returns are of an asset are normally distributed. So, which means that they are going to be following a normal random variable, and then because the normal distribution is symmetric, one would assume that this using the normal distribution to look at the asset return would be consistent with the actual distribution of returns. However, in practice, when you look at the returns and you look at the if you plot the histogram and then smoothen it out, then you notice that there are certain characteristics that are exhibited by the actual empirical data that are not consistent with the normal distribution, and I have identified 3 of them here. One of them, it is non-symmetric, that means it is skewed on one side. One of them is highly peaked. So, that means that the peak of the bell shaped normal distribution is much more in case of the actual in case of the actual empirical distribution. So, that means that the peak will be higher if you plot the actual distribution as compared to the normal distribution with the same parameters, and it has longer tail characteristics. So, compared to the thickness of the tails of the two distributions on both sides in case of normal distribution, in reality the distribution of returns will exhibit tails which are thicker than what you would get in case of a normal distribution. Okay, so next what we will do is that we will enumerate some of the distributions which are not normal, but which are closer to reality in terms of fitting what is going to be this non-symmetric and highly peaked and longer tail characteristic that are exhibited by the returns. So, accordingly some statistical distribution that capture these features are stable Parisian distribution, the students T distribution, mixtures of normal distribution, Poisson jump diffusion process, and finally log normal distribution, and we are going to discuss this log normal distribution in a little more detail. Okay, so just to do a recap, let us recall that for continuously compounded return, what did we have? So, we had that if the rate of return is say R t dot, and if the interest payments are happening m times in a year, then the compounding factor is going to be 1 plus R t dot over m raised to m. And if you want this to happen in the compounding happening in a continuous manner, you would recall that we had let m tends to infinity, and this gave us limit as m tends to infinity 1 plus R t dot over m raised to m over R t dot, and the whole thing raised to R t dot, and this limit came out to be e raised to R t dot. Now, remember, so let us see this in the context. So, this means that if you start off with an amount p naught, then you will basically get your p t to be equal to p naught into e raised to R t dot. But in order to ascertain the return is going to be given by a rate R t, so that p t becomes p naught into 1 plus R t. So, therefore, we can write that e raised to R t dot. So, equating these and these two terms and cancelling p naught, we will get e raised to R t dot is equal to 1 plus R t. And here R t is the holding period return. Okay, so therefore, we can say that this R t dot, so from this expression, this is going to be equal to the log of 1 plus R t. And what was R t? So, if you start off with, instead of p naught and p t, so when we are talking about holding period return, so we are actually considering some interval p t minus 1 to p t. So, we start off with, so actually I should be, let me just correct this for consistency, let me write p t minus 1, let me write this say p t minus 1, and I write this as p subscript t minus 1. Okay, so this means that my R t is simply going to be equal to p t minus 1 over p t minus 1. All right. So, then this means that this will give me that 1 plus R t is going to be simply p t over p t minus 1. So, therefore, log of 1 plus R t, this is going to be log of p t over p t minus 1. This is what we are known as the log returns. So, just to visualize this non-normal and normal, so this is what the normal distribution would look like. So, if I were to plot the return against the probability of that return based on historical data, if it was normal, then the data would fit this normal distribution curve. But in reality, it is going to be fit something like this. So, this is the log normal distribution. So, if I say that the asset returns are fitting a log normal distribution, it is going to look something like this as compared to the normal distribution. Okay, so now if R t dot has normal distribution with mean mu dot and variance sigma dot square, so that R t dot follows normal distribution with mean mu dot and variance sigma dot square, then the HPR, that is the holding period return, R t, this is said to have log normal distribution. All right. So, it is a HPR which is 1 plus R t or simply R t. Right. So, this brings us a definition of log normal distribution, that here if your R t dot follows a normal distribution with mean mu dot and sigma dot square, since this random variable is equal to natural log of 1 plus R t. So, then we say that this. So, that means that a natural log of 1 plus r t is going to follow a normal distribution. So, this accordingly I can say that 1 plus r t or its scaling, which is simply r t, will follow a log normal distribution. So, here the random variable under consideration is r t, and since natural log of 1 plus r t follows a normal distribution, and you remember that a normally distributed random variable is one whose log follows a normal distribution, and since here log of 1 plus r t follows a normal distribution, therefore, the random variable of 1 plus r t by definition of log normal distribution follows. So, 1 plus r t is a log normal random variate, and since 1 is just a scaling factor. So, 1 plus r t minus 1, that is r t, is also a log normal distribution. So, in reality what happens is that as compared to the returns, the holding period returns, if you fit empirically and if you fit it to a normal distribution, and if you take the log of the returns and you fit it to normal distribution, that means if you fit it to a log normal distribution, it is observed that the log normal distribution gives a more realistic fit to the empirical data as compared to the normal distribution. Okay, so I will straight away use a property from log normal distribution. So, then the mean and variance of 1 plus r t, remember 1 plus r t follows a log normal distribution. So, its mean and variance is going to be E of 1 plus r t. I will denote it by mu, and I will denote the variance of 1 plus r t to be equal to sigma square. Now, since this is a log normal distribution, so this will be given by exponential of mu dot plus half sigma dot square, and this will be given by variance is going to be given by, remember that mu dot and sigma dot, these are for r dot distribution, and mu and sigma square are for the 1 plus r t random variable. So, coming back to sigma square, this will be given by exponential of twice mu dot plus twice sigma dot square minus exponential of twice mu dot plus sigma dot square. Now, this will be given by mu square. Mu square means you would recall that this is mu. So, the mu square is simply going to be equal to exponent of twice mu dot plus sigma dot square. So, I am just making use of that here. I am taking out this factor, and all I am left with then now is exponential of sigma dot square minus 1. Also, the median of 1 plus r t is exponential of mu dot, and mode of 1 plus r t is exponential of mu dot minus sigma dot square. Okay, so now that we have talked about the properties of log normality in the context of recognizing the fact that the historical returns data based on the empirical analysis results in the historical data being more amenable and more realistic in terms of fitting the distribution to a log normal distribution as compared to a normal distribution. So, now that we have talked about the log normality of returns, let us now move on to the discussion on log normality in the context of portfolio analysis. So, therefore, we start this topic of portfolio analysis under log normality. Okay, so for this, let us assume that the returns are log normally distributed. Now, the continuously compounded return r t dot can be converted to the standard normal random variate. What is this? This is z subscript t, which is r t dot minus mu dot over sigma dot, and this follows a n01 distribution. Remember that your RT dot, that is the continuously compounded rate, followed a normal distribution with mean mu dot and sigma dot square. So, I have just done the transformation, we have already, or standardization. So, I just recall the concept of standardization when we had introduced aspects of probability theory. Okay, so this conversion or standardization renders the portfolio analysis much simpler. So, it makes the analysis much simpler. Now, RT dot, so we come back to RT dot is ln of 1 plus RT, that is natural log of 1 plus RT, and remember from here our RT dot can be written in terms of mu dot and sigma dot. So, RT dot is going to be mu plus sigma zt. So, this is going to be mu dot plus zt dot sigma dot, and so therefore, Wt, which is equal to W naught. So, I will now drop subscript t. So, Wt, which is equal to W naught into 1 plus R, remember this R is basically for the holding period return. This is going to be equal to W naught into e raised to R dot, which is the continuously compounded return, and this R dot from here I will get this to be W naught is equal to e raised to mu plus z sigma dot, mu dot plus z sigma dot. So, accordingly, to maximize the expected utility of the terminal wealth, the investor will choose the portfolio that will maximize the following expected utility equation. So, what is Wt? Wt is given by this relation. So, the expected utility of this will now be given by utility of Wt, which is W naught into e raised to mu dot plus z sigma dot, integral of this from minus infinity to infinity, and the probability density function. So, here the random variable is z. So, the probability density function is going to be f of z, and this integral is with respect to dz. So, we next determine how the return and risk affect the expected utility. All right. So, we will look at these 2 points in terms of sensitivity to return and sensitivity to risk. So, accordingly, we will start off with this form of the expected utility and take the partial derivative of this with respect to mu dot and sigma dot square. So, the partial derivatives of the expected utility with respect to, so we are the return, that is mu dot, this indicates the effect of maximizing return mu dot for a given risk class sigma dot. So, accordingly, using the chain rule, we have So, I will take the partial derivative of the expected utility of the terminal wealth with respect to mu dot. Now, the chain rule will give me the partial derivative of the expected utility of terminal wealth with respect to the terminal wealth multiplied by the terminal wealth partial derivative with respect to mu dot. Now, this is going to be given by, so first of all let me look at this term. So, I will take this partial derivative with respect to w t. So, I will take the partial derivative of this with respect to w t under integration sign. So, this will give me minus infinity to infinity del u w t over del w t into w t into f of z dz. Now, here we have used del w t del mu dot is equal to w t. All right. So, basically we have done the differentiation under the integration sign, which takes care of this, the partial derivative of this, and then f of z dz remains, and then for the remaining term here I have made use of this relation out here. Okay. Also we note that f of z being a probability density function is greater than 0, as well as del u del w t partial derivative of u with respect to t. Remember, the partial derivative of first derivative of the utility function is always going to be positive for a rational investor. So, accordingly this term is positive, this term obviously is positive, and f of z is always positive. So, this means that since all the terms are positive, so this is always going to be greater than 0. All right. So, now we come to the next point. So, the second point is we take the partial derivative now with respect to the sigma dot. So, the partial derivative of expected utility with respect to sigma dot indicates the effect of minimizing sigma dot for a given mu dot. So, again using the chain rule, we obtain the partial derivative of the expected utility of terminal wealth with respect to sigma dot. This again as before is going to be a partial derivative of the utility of the expected utility with respect to the wealth, and then we take the partial derivative of the wealth with respect to sigma dot, and this turns out to be integral from minus infinity to infinity del u del w t into del w t into w t z f of z dz. So, this is the same as before, except that now we will have this additional z here, and this can be, so which can be negative, positive or 0, right. So, remember that this is positive and this is positive, but we cannot, depending on what your z is, this entire term here can either be negative, positive or 0. Okay, so this brings us to the end of this lecture. So, just to do a recap, what we did today is that we looked at the portfolio theory in the paradigm of utility functions, and in particular what we did was we looked at an example of a quadratic function, quadratic utility function, and then we talked about the expected utility and its maximization, and we looked at a particular example where we motivated why a log normal distribution is a better fit to through the return distribution of any particular asset during the holding period return, and we looked at the sensitivity of the expected utility of that in terms of the expected return and variance of a continuously compounded convention being used. So, in the next class, we will continue our discussion on portfolio theory in the context of utility functions, and then we will move on to looking at certain criteria analogous to the mean variance criteria, but extended in this case to the non mean variance framework. Thank you for watching.